Hi there, folks. Today we're going to do the pen talk. And so the pen talk is a talk that I usually give in my calculus and biocalculus class once we've reached a certain point, usually once we're a little bit past derivatives. And it's really the talk which people have been wanting since they started learning math in grade school. It answers the question of why do we care about any of this stuff and how is it all connected? And so let's start with something simple. Consider this pen. How is this pen moving right now? And that's really the crux of the question. How is this moving, growing, or changing? And right now you can see it's kind of standing still. There's an air show going on, so there might be some movement just from vibrations from that. But we can also think of this on a micro and macro scale. When we think about this pen, we can think about this pen as being on my desk. And on my desk, well, my desk is currently on the Earth. And the Earth is currently rotating. And as the Earth is traveling, it's traveling through space on the sun, or not on the sun, but around the sun, as the sun is going through the galaxy, as the galaxy itself is going away from the center of the universe. And so we can think about it in that respect, but we can also think about how it's moving internally. I mean, there are, well, not countless, but a ton of atoms in there, a ton of molecules in there, and they're all vibrating, they're all interacting. It's a solid, but there's still a substantial amount of movement just within this pen. And the thing which is tying all of these things together is the idea of forces, whether we're talking about forces at the micro level or forces at the macro level. And we can ask the question of, what are these forces? Well, ultimately, from a physics perspective, we can think of the force as a vector, which is equal to the mass times acceleration, which is also a vector. Well, we don't have the idea of vectors yet, but what we do have is this idea of acceleration. All that acceleration is the second derivative. And once we have this idea of the second derivative, well, we can see that the things which are guiding the movement of that pen at the micro and macro scale are all tied to this idea of the second derivative. And so whenever we want to model anything related to them, whenever we want to try and understand the motions of this pen or of any object, we can really just think about this second derivative. It turns out that anything that moves, grows, or otherwise changes can be modeled based on the derivative, or the second derivative or higher order derivatives, but it's all tied to this idea of the derivative. And so we can take this idea of the second derivative and go and just look at what happens when we set the second derivative equal to some basic motions. And really, there are three very simple differential equations which we can consider. Differential equations being equations which are related to the derivative. And I'll write these three down. The first one is y double prime is just equal to some number. Let's call it k. The second one would be y double prime is equal to y, or some scalar multiplied by y. The third is saying that the second derivative is going to be proportional to the opposite of y. So there's a negative sign in there. And these three define the motions of most things. And so let's see if we can understand the types of things that are going to be, or the types of equations which occur when we're looking at these three examples. And again, remember, everything that moves, grows, or changes it's tied to these three equations or variants of them. And so let's start with this first one. Y double prime equals K. What functions have a second derivative which is equal to a number? And what we see is we see quadratics. We see linear functions. Quadratics and linear functions, as well as constant functions, are all going to have a second derivative which is equal to a number. This is where we get a lot of our Algebra 1 ideas from. It's from just trying to understand quadratics and linear functions. And in order to understand these functions, we need a lot of tools because we want to make sure that we understand the bigger ideas in the form of polynomials. We want to make sure that we understand how to solve for different variables, which means we're going to need radicals. And we're going to need rationals. And so all of these different components are used to understand this one model. This, by the way, would be represented by a baseball being thrown in the air. Simple gravity. What goes up must come down, a parabolic trajectory. All of that is tied to this one differential equation. The next one's a little bit trickier. And so y double prime is equal to k times y. What function is its own second derivative? And it turns out there are a couple. They're both very similar though. One is going to be exponential growth and the other is exponential decay. If we have y equals e to the x, the second derivative is going to be y equals e to the x. If we have y equals e to the negative x, well, the second derivative is going to be y equals e to the negative x. So here we have exponentials. Both growth and decay. And how do we solve things which have exponentials? Well, we need our logarithms. And so while this first one was all about Algebra 1, Algebra 2 really goes and does a dive into this. We can't really understand these without the idea of functions, though, and so typically functions are introduced in Algebra 2. They might be introduced briefly in Algebra 1, but they aren't really gone in depth until Algebra 2, where we start to say, all right, we can think of all of these things as functions, we can think of these as functions, and now we can have a better understanding of all of these different objects. Oh, the other thing that will fall into this category is the hyperbolic trig functions. You might not see these that often. But what the hyperbolic trig functions are is they're functions which are really a combination of the exponentials. And so if you have the sinh function, for instance, sine h of x, that's going to be e to the x minus e to the negative x over 2. It's literally just a combination of these two objects. The cosh function is the same, but with a plus sign in there. And then all of the others follow the same guidelines as the trigonometric functions. And so you'll often see the hyperbolic trig functions pop up when we're talking about this. And exponential growth and decay, that happens whenever you have a population which is proportional to its rate of change. And so when you're talking about things like bacterial growth, when you're talking about things where things are growing or things are shrinking, it's usually going to be following some form of exponential growth. And it's going to be tied to this relation here. Then there's this third case. And so what function has a second derivative, which is the same function, but a different sign? And I guess technically this should be a negative k squared so that we can verify that it actually is a negative value. But what function has that property? And I guess this one should also be a k squared, but we're not going to stress squares. There we go. And the function you should be coming to is sine and cosine. When you take the second derivative of sine, you get negative sine. When you take the second derivative of cosine, you get negative cosine. And so right there, you get your sine and cosine. Well, how do we solve equations which have sine and cosine? We use our other trig functions. And we use our inverse trig functions. And so these are the three simplest differential equations. And by comparison to things which you'll see in the real world, they are very, very simplified. These things can get much, much more complicated, in particular when you start including more terms or more outside influences. For example, when you start thinking about things like predator and prey models, a predator and prey model will consist of multiple components. And so you'll have things like rabbits and wolves. And we actually have the ability to develop a model for rabbits and wolves fairly quickly. If we think about the rate of change of rabbits versus the rate of change of wolves, well, we know that when we have rabbits and no wolves, we're going to get exponential growth from rabbits. And so we might have an AR term. We also know that the interaction of rabbits and wolves is going to have a negative effect on the population of rabbits. And so we might have a B times RW, where R and W are both functions of time, by the by. So we'll say R of t and W of t. For wolves, if you have no rabbits and only wolves, your wolf population is actually going to starve. And so let's put a CW term in here. And then the interaction of rabbits and wolves actually has a very positive effect on the population of wolves. And so we'll get a system of differential equations which looks something like this. And as soon as you start trying to understand how these things are interacting with one another, well, rabbits and wolves interact with one another. You're actually going to see that there's a cyclical behavior that occurs from a differential equation like this, which is largely tied to the idea of the exponentials affecting the rabbits and wolf population here with exponential growth and exponential decay, as well as this RW term actually leading to some interesting sine and cosine behavior, where you will start to see things start to oscillate. You'll get seasonal behavior, you get long-term cycles, and then you can also start to say what happens when you have additional components. For instance, what if in addition to rabbits and wolves, we introduce field mice, which might be a competitor to the rabbits for food, but may not be a viable food source for the wolves. That will drastically change the way that this function works. If you're going into ecology, you need to be able to understand how all of these functions come together to understand a system like this. And if you're going into biology or medicine, you need to do the same. You need to be able to understand how different chemical compounds are moving from one area to another. You need to be able to understand how a circulatory system works. You need to understand how the kidneys work. And you need to understand how different populations affect other populations. If you're going into physics or engineering, same thing. I mean, you need to be able to understand how all of the different forces are going to be acting on whatever object you're dealing with. If you're going into economics, it's the same stuff. It's all about the rates of change of different amounts and how you can model those rates of change to determine short-term and long-term behavior. And so everything that we've done up to this point has kind of led to this set of functions, our algebra 1 functions, our algebra 2 functions, and our trigonometric functions. All of these come from these three simple equations, and they create the basis for all of the mathematics that you've learned so far. Up until this point, you probably haven't been told how all of these functions are connected. Why is it that we care about the way that the trigonometric functions are defined based on the unit circle versus the number e, and why we care about the number e, and how it's all related to quadratics and polynomials? Well, this is the answer. Everything in the universe can be modeled using these functions, these core functions which we have developed. There are additional ways to model things, but these will get you really, really far. And that's the pen talk. The pen talk starts with the idea of something simple. How does a pen actually move? And it develops into this idea which unifies all of mathematics. And so as you're going forward, you want to make sure that you feel very comfortable with these core functions. You want to make sure that you feel really comfortable with your derivatives and your antiderivatives. And you want to try and figure out how you can develop models like this. As you go out into your field and become researchers, you're going to be developing models like this. And it's very important that you get your modeling correct. Hopefully you've enjoyed this talk.